How a microcontroller is made. Every day, whether enough people are aware of it, the experience process is controlled by integrated circuits. Infineon. Infineon Technologies developed logic and memory components around the globe. Experts in research and development centers are working on new semiconductor and system solutions productions that take place in leading edge manufacturing facilities worldwide. Up to 1 billion transistor functions fit on a silicon chip, only 1 square centimeter in size. The watchword for the future: smaller, faster, and more efficient. Now look at the video how to make a chip. This is the raw material. Chips are made of sand. It is made up of silicon dioxide. Silicon is the second most common element on the earth crust and only exists in bonded form. Complicated chemical and physical processes are needed to convert silicon into a crystalline form and make sure the crystal will meet all the requirements necessary for chip production. The final product is a monocrystalline silicon rod of highest purity. This means the rod has only one impurity atom for every 10 million silicon atoms. Silicon is a semiconductor. Its atomic structures look like this. Each silicon atom has 4 outer electrons. There are no free charge carriers. The pure silicon monocrystal is a non-conductive at room temperature. To make a conductive, small quantities of specific impurity atoms, such as phosphorus, are built in. Phosphorus has 5 outer electrons. The 5th phosphorus electrons built into each molecules of the silicon crystal lattice can move freely. Because of this structure, the silicon phosphorus crystal is negatively charged or N-conductive. N-conductive boron atoms, on the other hand, have only 3 outer electrons. When they are built into the silicon lattice, one silicon electron is missing. These create electron holes. They move through the crystal like positively charged electrically particles. The material is positively charged or pre-conductive. The transistors in modern memory chips are constructed from P and N conductive layers, such as these transistors are the smallest control units in the microchip. In the heart of an NMOS transistor, for example, we find P and N conductive layers of silicon crystals. An additional layer consists of silicon oxide and act as an insulator, a layer. A layer of electrically conductive polysilicon is applied on top of it every transistor. Because every transistor has 3 connections, the middle one is attached to the gate, the electrically conductive polysilicon. If we apply an electrical charge only to the 2 outer connections electrically, is unable to flow the transistor. Transistor is blocked. Things are different when an additional charge is attached to the middle connections. The electrons from the P layer now attached towards the middle connections and accumulated at the border area between the silicon crystal and the insulation gate oxide. A channel through which the electrons can flow is formed between the island of N-conductive material. The electrical circuit is closed. The transistor can be switched back and forth between current off and current flow, that is to say between 0 and water. This binary system. Binary system is the basis of electronics data processing. One highly complicated component, for example, is this dynamic 1 gigabit memory chip on an area of only 1.3 centimeters. It can store the contents of 64,000 standard size sheets of paper. If it were constructed of conventional components, it would cover the area of a small town. Layout and designers at the beginning of chip manufacture. The large number of components call for an elaborate design process to define the circuitry functions of the chip. Next, the technical and physical characteristics of the chip are simulated. Up to 1 billion transistors per chip are connected with the aid of wiring tools. The design tool forms the connections to a 3-dimensional architectures of sandwiched layer. This constructions plan is transferred to mask. These are reprographic stencils for the subsequent manufacturing process. The cover precision for the mask is monitored by the measuring machines which can detect deviations in the range of 100,000 of a millimeter. The finished marks of the geometric image of the circuits that are exposed one after another in several production processes. The flawless productions of microscopically small structures calls for a virtually dust-free environment in which the temperature and humidity are stable. The clean room meets these requirements here in 10 liters of air. There is a maximum of only one dust particles large. The ventilations, filtrations and supply area in the clean room is extremely elaborate here. 5.2 million cubic meters of air are circulated every hour. 100 of air volume regulators maintain a constant airflow. The silicon wafers are transported from the 300 mm fabrications in hermetically sealed containers clean room inside the clean room. So to speak, this helps reduce costly filtrations technology. The high technological standard closed material circuits and energy reclamations keep environmental stresses to a minimum supply. Minimum supply systems with special containers and filters maintain the extremely high purity of the chemicals. The basic material for the chips is a 1 mm thick silicon wafer. This is tiny cutout of a wafer edge 1/4 of a micrometer. First, the conductive or non-conductive layers are produced by oxidations of the surface at approximately 1000 degrees Celsius. In a high temperature furnace, a drop of photoresist is uniformly distributed by centrifugal force on the oxide layer produced, thus creating a light sensitive layers. Special exposure machines, so-called wafer steppers, transfer the mask by exposures to the silicon wafer. The accuracy of adjustment to the features already produced must remain within a tolerance of 1/100 of a micrometer. Next, the photoresist coated wafer is exposed through a mask. The exposed selections can be developed while the unexposed features remains. The oxide layer is etched. Of this etching process is carried out either by wet etching or plasma etching. In plasma etching, special gases combined with the layer to be removed. This makes it possible to remove the microscopically thin layers inside the windows created by exposure development and etching. After dissolving the remaining photoresist and then cleansing, another oxidations take place. This time a very thin layer is affected. Electrically conductive polysilicon is deposited on this insulations layer. Then once again photoresist mask and exposures occur and the exposed photoresistor is again dissolves. Then the polysilicon and the thin oxide layer etched off, they both remain intact only in the middle under the resist layer. In the next step, an ion implanter shoots impurity atoms into the silicon. This changes the conductivity of the exposed silicon by fractions of micrometer. Structure, width, distance and cover precisions are constantly checked. After the residual photoresist has been removed, another oxide layer is applied. Once again, the cycle of photoresist exposure, removal and dissolutions takes place. Contact holes are etched into open up access to the conductive layers because the contact and interconnections must now be deposited. For this purpose, metal compounds are sputtered onto wafer sputtering machines. Once again, photoresist and mask, depending on the component, over 200 meters of interconnections are created. The unexposed strips show the path of the aluminum conductor tracks that remains behind after the etching process and provide the contact to the underlying layers. More and more often aluminum interconnections are being replaced by copper ones because the outstanding electrical conductivity of copper guarantees an extremely high data transfer rate. The insulations layer above the interconnections must be given a smooth surface, which is why the CMP, the chemical mechanical process, is used excess material and the micrometer range is polished off. In this production line, the individual work processes are repeated 4 to 500 times until the integrated circuit of a component is completely assembled. 501 gigabit chips have been produced on a 300 mm silicon wafer. None of these chips is any larger than a single key on a computer keyboard molded into a plastic housing. The microchip is used for several thousand applications. Over the past few years, the chip connections have changed considerably. On the first plastic microchip housing hole still had to be drilled in the printed circuit boards. The later housing can be directly soldered to the surface to save space in the circuit boards. The connections in the latest constructions form are located on the undesired of the components. This way, over 1,000 connections contacts can be released. The third dimension is already being used for highly complex logic components. Sandwich components chips are supplied as complete units. All the production phases of chip are controlled by research and developers using scanning electron microscopes. The comparison with a human hair shows us the dimensions of today's microelectronics. The checking and flow analysis equipment is just precise. For test purpose of focused iron ray drills precise holes in the connections, allowing interventions into the completed circuitry. The supplementary interconnections being inserted into the circuit here is only 1 micron wide. Chip development has become pacemaker of our economy. Microelectronics is the key industry of our modern information society. Thanks to microchip, mobile worldwide networking makes everyday professionals' life easier. The technological accomplishment of modern telecommunications depends primarily on progress in the semiconductor industry.